Hey guys, I wanted to do just a quick chemistry review with you, just to make sure that we're all kind of caught up with things. Actually, I think we're probably going to do two. So we're going to start off talking about different kinds of bonding, covalent bonding and ionic bonding and stuff like that. And then we'll move into structure of water and hydrogen bonding and stuff. So just a quick little review here. Matter is anything that takes up space, has mass. An element is something that can't be broken down anymore. So you could have 2 pounds of gold, and you divide that in half, and you get a pound, and you divide that in half, and you get half a pound, so on and so forth. And you go all the way down until you only have one atom of gold. Now, here's the thing: that one atom of gold shares exactly the same characteristics as that 2 pounds of gold. It's all the same. It has the same conductivity. It has the same melting point. It has the same color. It has the same mass. Anyway, you get what I'm talking about. So a compound is just two or more elements that are combined together, like hydrogen and oxygen to make water, or in this case, like sodium and chloride to make salt, table salt. Um, Most of the things that we're actually going to be talking about in here are made up of carbon, hydrogen, oxygen, and nitrogen, with a couple of other things kind of thrown in, a little bit of sodium, a little bit of chlorine, a little bit of potassium. Oh gosh, what? Oh, a little bit of calcium. Both of these are ions. Anyway, um, that's mostly it. There's not a whole lot of other stuff that's actually going to be making up like your cells. So in chemistry, you have to know a whole bunch of different kinds of elements. In AP Bio, you need to know six, maybe seven, and that's pretty much it. Um, when you're looking at periodic table, just a couple of things. There we go. The atomic number is the number of protons. If you change the number of protons, you change the element. So if you've got something that has 28 protons in it, it's nickel. If you somehow squeeze another proton into that, it actually becomes copper. So it physically changes everything about it, the color, the conductivity, the melting point, all of that sort of stuff changes. Carbon has 6 protons in it. If you add another one to it, it becomes 7. If you take one away, it becomes boron. So the atomic number is what actually makes the atom or the element itself. Elemental symbol. You can use these things on AP exam. You don't have to spell out the whole elements or anything like that. If you're talking about helium, just put helium and they'll know exactly what you're talking about and they're good with that. Atomic mass is the average number of protons plus neutrons. And the whole, like normally it would just be a whole number, but if you look on every little atom that's on the periodic table, there's always a little bit extra. And where that comes in is that every once in a while, for example, helium has 2 protons and typically 2 neutrons, so it should have an atomic number of 4. Every once in a while, you'll actually have one that has 3 neutrons instead of 2. It's really rare. I mean, as you can tell by looking at that number, 4.003. It's not very common, but there are some that have that, and those are called isotopes. We'll talk a little bit more about isotopes later. Um, yeah, we don't even need to really even get into. Actually, yeah, I do want to talk about one thing. The periods, the rows that go across. Okay. Those are important only because it tells you how many electrons are in the outermost ring. So, for example, in the first period, there's only 2 in that first valence ring. And you can tell that because right here, there's only hydrogen and helium there. Now, in the second period, there's 8. There's 1, 2, 3, 4, 5, 6, 7, 8. So, what the periodic table is set up to show you, one of the many things it's set up to show you is how many electrons are actually in that outer ring, so you can tell how many times it actually can bond with something else. Um, this down at the bottom of the page, right there, is what we call a Bohr model. It was named after Niels Bohr, and it's not really accurate. It's sort of a lie to children where we say that electrons kind of zing around the nucleus of an atom in these sort of orbitals, like you'd see. I mean, like the first orbital holds 2, the next one holds 8, the next one holds 8, and so on and so forth as you actually move outwards of that. Um, and that's partially true. They are found in these groupings, but they're not nearly as neat and organized as the Bohr model makes you believe. If you took chemistry, you know that they're typically in like electron clouds. So it's not quite as neat and tidy. But even though this is a lie to children, it's a pretty good lie to children. So we're actually going to stick with it because not because it's accurate, but because it sort of seems to make sense. And that's just an easier way of looking at things. Um, a simplified Bohr diagram, actually, let me back up here. So you see how this one actually has all of the rings involved. For example, lithium has 3 protons, so 3 neutrons. Let me show you, let me zoom in here and show you, we'll do carbon. And carbon has 1, 2, actually it has 8 protons. I'm sorry, 6 protons. So it has 6 electrons. So that first ring holds up 2, and then the outermost can hold 1, 2, 3, 4. But here's the thing, drawing all of those in there sort of gets tedious. Sodium, oops, I didn't mean to do that. Sodium has a bunch. It actually has 11. So if we wanted to draw that out, let's go back to that thing there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's supposed to be a circle. 11. All right. So that just kind of gets tedious, just drawing all of those inner rings and stuff out. And so there's sort of what we call a Lewis dot model, and it's just kind of a condensed Bohr model. All we really do is we just care about what's in the outermost ring. That's where that periodic table comes in, and it's so important. So I said lithium has 3 protons. Well, the first ring only has 2, so that outer ring holds. Oops. Oh, my cool handy circle maker is not working too well. Anyway, that outermost ring can actually hold 8, but there's only 1 there. So just to make things a little bit easier, we just draw that. Now, why this all matters is that elements want to behave as if they're noble gases. And what I mean by that is that the outermost valence shell wants to be completely full. All of the noble gases from helium to neon to argon all the way down. I'm a biologist. I don't know anything bigger than that. Anyway, um, their outer rings are completely full. So if you have something like neon, I keep doing that. You have something like neon, its outer ring structure, if we use the Lewis dot model, would look like that. It's completely full, it's stable, and therefore noble gases don't react very easily to anything. You can sort of force them to. For our purposes in biology, we can just say that a noble gas is completely stable. And that's what everything else wants to be like. Um, so how they'll get to that is by either sharing electrons with something else or by gaining or losing electrons and becoming charged particles, becoming ions. And that's kind of what we're going to talk about here. So with a covalent bond, you can see, yeah, okay. You can see down here, oxygen has, let's see, where do we go? It actually has 6 electrons in its outermost ring. It has 8 protons, so oxygen has 8 protons. The first ring holds up 2, and then you have 3, 4, 5, 6, 7, and 8. So when we look at oxygen, oxygen actually has 2 places that it can share electrons. There's one electron, there's another electron, and it can share both of those. In fact, both of these oxygen atoms here can each share an electron. And what we wind up with is something that looks like a double bond. Let's see. Let me show you something here. I'm just going to add one in. So we'll look at carbon. Okay. So carbon has 6 protons. So it goes 1, 2, and then 1, 2, 3, 4. Now, if it wanted to share its electrons with something like hydrogen, that's all cool. It can share 4 electrons with 4 hydrogens. And now this carbon feels like it's a noble gas. It feels like neon. And each of these hydrogens feels like a noble gas. It feels like helium. Okay. An easier way of writing this is just to draw a line for each shared pair of electrons. So that is CH4. That's methane. Here's another one, ammonia. Nitrogen is another really common element that we're actually going to see. It has 7 protons, so therefore if it's neutral, it has 7 electrons. So just like carbon, there's 1, 2, 3, 4, 5, and then in the middle it has 6, 7. But here's the important bit right up here. That one, that bonding point you see with carbon to the left, it had 1 electron up there that it could share with hydrogen. This nitrogen is already filled it. So really there's only 3 spots that it can share electrons with something like hydrogen. This looks like that. That's ammonia. And then what we just saw was something like oxygen. Oxygen has 8 protons, so 1, 2 right in the middle, and then 3, 4, 5, 6, 7, and 8. So both of these spots are already completely filled. So if it wanted to share electrons with something like hydrogen, it could do that. Now oxygen feels like it's full, hydrogen feels like it's full. That's water. That's why oxygen only bonds to 2 things. It only bonds to 2 hydrogens. Now, as we saw back here, you can not only bond to something like hydrogen, you can actually double bond. Let's change the color so you guys can see it. You can double bond to another oxygen. Um, when oxygen bonds to itself, that's oxygen gas. Now, what you're actually seeing over here is water. I already showed you that before. Water sharing these electrons with hydrogens. But here's the thing. When oxygen shares electrons with something as small as hydrogen, it tends to gobble things up. It tends to gobble up electrons really well. So this oxygen really, really, really likes electrons. And so because of that, those oxygens or the electrons tend to be closer to oxygen, and it has a net negative charge on the oxygen side and a net positive charge on the hydrogen sides. What we do is we say that this is a polar covalent bond. They're sharing electrons, but it's a polar charge, meaning it's a polar compound, or so it's a charged compound. Some ionic bonds. Here's some interesting stuff here. In fact, let's go back here and erase all this, and I'm going to show you things like sodium and chlorine. So sodium has 11. I showed you that before. So it's got the 1, 2, and then 3, 4, 5, 6, 7, 8, 9, 10, 11. And the thing is, sodium would have to completely fill up this outer ring with 7 more hydrogens if it wanted to covalently bond with something else. And it's just not worth it. It doesn't really, that never happens. So it cheats. It just gets rid of one of those, oops, um, gets rid of one of those electrons, but now it actually has more protons than it does electrons, so it actually has a +1 charge. So chlorine is just the opposite of this, really. Chlorine has 1, 2, let's go back to my fancy circle drawing tool that probably won't work. 3, 4, 5, 6, 7, 8. It has 17, 9, 10, 11, 12, okay, 13, 14, ooh, 14, 15, 16, 17. Oh, we're missing just one. It literally only needs one electron to be happy and stable. So kind of like what sodium did just by giving up its electron, chlorine just kind of cheats and it just steals an electron from the environment. Well, now it has more electrons than it does protons, so chlorine has a -1 charge to it. So sodium is in its unnatural form, basically in its unionized form. It's a metal that it gives up its atoms so quickly that it explodes when it touches something like water. So sodium, with the +1 charge, combines with chlorine with the -1 charge. Chlorine gas, if it has that extra electron sitting around there, is unbelievably reactionary or reactive. It melts your eyes and lungs. If you have a pool and you've ever had to put like chlorine tabs or something in, then you know that you get too close to the bucket with chlorine and it burns. So you get something like sodium and chlorine, and you stick those two things together, you get sodium chloride, which is actually table salt. So you have a metal that explodes if you drop it in water, a gas that melts your eyes and lungs. But when you combine them together, they take on a very, very different characteristic. And they combine because of their charges. Now, so we've got covalent bonding, we've got ionic bonding. Now we're going to talk really quickly about hydrogen bonding. And what happens with hydrogen bonding is where you actually have two charged compounds, something like water, two water molecules or something that are close to each other. There's sort of an attraction between the negatively charged oxygen and the positively charged hydrogen. And so they sort of stick together, kind of like magnets, sort of like what an ionic bond is, except instead of just between one or two atoms, you actually have a bonding between whole molecules. Usually this happens when something like oxygen, nitrogen, or fluorine combines with some hydrogens because the hydrogens are so small, they really don't have the ability to hold on very closely with their electrons, and oxygen, nitrogen, and fluorine tend to be really kind of greedy when it comes to that. And so what you'll get, oops, let me come back here and show you just something just real quick. What you'll get is something like oxygen bound to these two small hydrogens, and the oxygen tends to absorb a lot of the electrons, and so this end tends to be kind of negative and this end tends to be kind of positive. Well, if we have another water molecule down here that has the same charges, now we have a positive and a negative charge. These things actually sort of stick together. And you could do another one down here or whatever. So water actually tends to stick to itself. All polar molecules tend to stick to themselves. Not only that, they tend to be able to dissolve charged particles very, very well. And we'll get to that next time. Thanks for listening.